Hi, this is the final video that I'm posting for my Year 10 GCSE students, debriefing the mock exam questions. And so we're looking at question 5 this time. This is the circuit that we're presented with. As you can see, we've got a transistor. And the transistor is working as a switch, turning the lamp on and off. Okay. So there's quite a little bit of background knowledge to answering the questions here. So if during the video I diverge from just directly answering these questions, maybe giving you a little bit of theory, I hope you do stick with it. So it's going to be used as a switch. The transistor is going to be used as a switch. So let's just first of all consider what happens when we have a switch in the circuit. So if we've got, say, 6 volts, and we've got a lamp, and we've got a switch. So that's my lamp, and we've got a switch, and the switch can have 2 states. It can either be open or closed. And so we've got 6 volts of potential difference between these two. And we've got the lamp, we've got a switch. Switch is open, so no current can flow. Hopefully that makes sense. You can't have current flow if you've got the switch open. Now, as you know, with Ohm's law, V, I and R, if we want to find a voltage change, we can just cover over V, and then we can then say, well, V equals IR. Well, if the current is 0 at this point, then the voltage change across this resistance, because there will be resistance in the lamp, the voltage change will be 0. Okay, so if I were to put a voltmeter across there, you'll actually find that voltage change. The difference, well, there is no difference because it stays the same, because remember, V equals IR, and if you've got 0 current, whatever the resistance, whatever this resistance of the lamp, the voltage change can be, well, no change. Okay, so if we start with 6 volts there, then we still have 6 volts there. That means that the potential between these 2 points, okay, across the switch, in other words, that potential is still going to be 6 volts, because we've got 6 volts of difference between 6 and 0 volts. So that's when we've got an open switch. Now remember, although we're not directly talking about switches in this question, we are talking about transistors as a switch. So we could consider this to be the collector and this to be the emitter of the transistor. Okay, so that's the first sort of scenario that you can have with a switch. So let's consider the alternative, which is when the switch is closed. So there we've got lamp, and we are going to close that switch this time. So the contacts of the switch are closed. And so this time around, hopefully you can see that yes, you can have current flow. So there will be current. And because we've got current and we've got a resistance in the filament of the lamp, then if we were to measure the voltage drop, we will also have a voltage drop. And in this particular case, we're going to have the full supply voltage. There's no other resistance anywhere else. So we'll have this full supply voltage drop across that, which will be 6 volts. So if we start at 6, then we drop by 6, then we're going to be at 0 volts there. And so, as hopefully you can see, that difference between 0 volts at this point in the circuit and 0 there that's going to be 0 volts. Okay, so if that were the collector and that were the emitter, VCE in this case is going to be 0 volts, ideally, assuming that there's no resistance in that switch. And in this particular case, VCE is going to be 6 volts. Okay. Remember, these are ideals. These are not necessarily exactly what you'd have in a real circuit, but you know, these are idealized models of using a transistor as a switch. Okay, so maybe that helps you a little bit. Let's so we've now considered at least, you know, the part of the operation of a transistor as a switch. But then they've given us this other thing about the input voltage V1 is V1 here of 0.2 volts. So let's just jot that in, and we'll now think about why that is important. So a transistor is a current amplifier. So the more current that we have into the base current, I sub B, the more base current that we have, then we can have the more collector current. Okay, so it's an amplifier of that current. But to actually start conduction between the collector, let's just note these in, that's collector, emitter and the base. Before we can actually have conduction between the collector and the emitter, we actually have to bias the base, so we have to have V2. We have to have V2 at about 0.7 volts. Okay, it's going to be very roughly 0.7 volts, but it's going to be something like that. So we normally just approximate, say, 0.7 volts. Let's now just consider that. So if we've got VCE, the voltage between the collector and the emitter, and then we've got V in here, that when V in is very low, okay, so when V in is very low, if we're starting at 0 volts, when V in is very low, the collector emitter voltage is going to be the full supply voltage. So, it's like this scenario here, that we haven't yet managed to turn the switch on, we haven't yet managed to close those contacts, and therefore the VC is going to be high. And then we then at a higher voltage level, input level, then we can get the VC to drop right down. Ideally 0, but it's not going to go actually to 0. Now there is a bit of an intermediate state which GCSE doesn't really consider too much, and it's between the two switch states. Okay, so in this state, or in this region, we could call this one cut off, because we cut off the current. In this one, we call this one saturation. And this middle region, just for completeness, I will call that linear. We don't learn much about that, if anything, in GCSE. If you do A-level electronics, and you learn more about that. But as we only use it as a switch, we either want to be in cut-off or we want to be in saturation. And ideally, we don't want to be in this like halfway switch, not quite fully on or fully off. So when does the switch actually get like properly turned on? So about 0.7 volts. All right, so that's important. Now, if you're very low on the input voltage, then there's insufficient voltage that's going to be over this base emitter junction. This is going to act a little bit like a diode. We'll talk about that a little bit more in a moment. And there's going to be insufficient current flowing as well. Okay, and remember this is a current amplifier. So let's just quickly think then about the 0.7 volts in relation to diodes, because the base emitter junction is a little bit like a diode. In fact, even the bar, that symbol looks a little bit like a diode. Remember, a silicon diode looks something like that. And current would normally flow just in that direction, forward biased. Okay. So when you have a diode, and let's just have the characteristic curve of current on that axis, and then on this axis we will have voltage, and at very low voltages you will have low current, okay, or next to no current flowing through. But when it suddenly gets to around about 0.7 volts, okay, 0.7 volts, and suddenly that starts to conduct. But until you've got like 0.7 volts here, you're not actually going to be pushing any current through. But as soon as you get to that 0.7 threshold, then current can start to flow. Now, there's a lot of stuff there, but hopefully that's actually going to arm you to be able to answer some of these questions. So if we've got 0.2 volts, we haven't yet reached, we know we can't yet have reached that 0.7 volts bias point to actually get a significant amount of current flowing across the base emitter junction. And do remember as well that not only could that input voltage be dropped across that junction, but also once current's flowing, there's going to also be some voltage drop across here, because if you've got a resistance and you've got current, then you've also got a voltage drop. So the transistor is currently switched off. So basically, like, the bulb is off. There's no current flowing here. There's insufficient current to be, insufficient voltage for any current or significant current to be flowing between the base and the emitter. And because of that, there's not going to be any current flowing through here. Okay, so if we were to consider the voltage drop, that if we haven't got any current flowing through here, or next to no current, then we're also going to have very little voltage change across here. And so if there's no voltage change, if we apply 0.2 volts here, we're still going to have 0.2 volts here with respect to ground. So V2 at this point is going to be 0.2 volts. In other words, the voltage is going to be unchanged. V3, remember they said that the transistor is switched off. In other words, it's an open circuit, which is going to be like, let me just show you again. It's this one with the open circuit. And when you've got the open circuit, no voltage change across the load, the lamp, and so the full voltage remains across the collector emitter junction. So where are we? Yep, V3. So V3, which is, I mean, that is the same VCE, voltage between the collector and the emitter. That is going to be the full supply voltage of 6 volts. Okay, hope you're keeping up on this one. The lamp is rated at 6 volts, 180 milliamps. Calculate the power dissipated in the lamp when it's switched on fully. So when it's switched on fully, then you'll have no voltage dropped across the collector emitter. So the full voltage drop will be, full voltage supply voltage will be dropped across the load. They've already told you that that is 6 volts, it's 180 milliamps. So we can just calculate the power, and power equals VI or IV, whichever way around you want to state it. And so we'll say 6 times 180 milliamps, and then you could have just written 180, but then you might have got like a little bit confused and forgot that you weren't working in amps or something like that. So let's just quickly type that in. So 6 times 180. Which gives us 1080 milliwatts, 1080 milliwatts. Okay. The other way you could have done it, you could have said 6 times 0.18, so that's 6 times 0.18 amps, which is the same as 180 milliamps. But if you do that, then you'll get 1.08 watts, and remember that they had expected the answer to be in milliwatts. Okay, hopefully that's okay. The input voltage is changed until the transistor is saturated. So what they're saying here is that we're increasing the voltage like this until we reach saturation. Now the point is that you could carry on increasing the input voltage, but once you carry on increasing the input voltage, then the voltage across the base emitter junction pretty much stays at about 0.7 volts. It will increase a little bit, but it will pretty much stay across the base emitter at 0.7 volts. But then the remainder of whatever you are applying at V in will then get dropped across this. So for example, if you apply like, I don't know, like 5.7 volts to V in or V1, then you'll have 0.7 volts dropped across here and 5 across here. If you increased it to 10.7, it will be still 0.7 here, but then 10 across that, like that. The input voltage is changed until the transistor is saturated. Transistor has a current gain of which is also known as HFE, of 90. Okay. Now, what that means is that when we are in just entered saturation, and they give you the current, where was it? Oh no, they haven't given you the base current. They've given you the current, the collector current. The relationship between the base current and the collector current are very, very easy to calculate. Okay, so the formula for that is going to be, in fact, let me just quickly find the way that they've arranged it. So here we go. So the collector current is equal to the gain times the base current, which in other words means that, let's say if you're, like you've got a base current of 1 milliamp and you've got a gain of 100, then be 100 times 1 would give you 100 milliamps in the collector, for example. So IC equals HFE, and then multiply that one by IB. All right, now we need to calculate IB, so we need to rearrange this. So we're going to say that IB equals IC over HFE. All right, so now IC is, what was it? IC is 180 milliamps. And we need to divide that by the gain, which was 90. So that's going to give us 2 milliamps. Okay, so and they've already given you units, milliamps, so just write that 2. The voltage VB across the base resistor. So what have we got here then? Well, we're going to have 2 milliamps. So they don't actually tell you what the input voltage is, but they do tell you that we've calculated that we got 2 milliamps flowing through, not only through the base, but that same current is going to be flowing, because that same current is going to be flowing, through there, down through the base emitter junction and down there. Okay, so if we know that this is 2 milliamps, which we just calculated, and we know the current, then we should be able to calculate the voltage, because V equals IR, and so if we know that the current is 2 milliamps, and we know the resistance is 1 kilo ohm. Now, the milliamps is thousandths, and then K is thousands, so we could just cancel those out. So basically it's 1 times 2, which is going to be 2 volts. Okay. Now, if you didn't quite follow what I was talking about there, what I'm saying is that is 0.002 times 1,000, okay, which gives you 2 volts. The other way you could have done it is 2 times 10 to the minus 3 times 1 times 10 to the 3, and then that cancels out. So then you've got 2 times 1, which is still 2. Okay, hopefully that makes some sense. If I do it several ways, then you just choose whichever way you prefer to do. Right, how are we doing for time? Well, I can't see on. I haven't figured out actually with this recording software as to see how long the video is so far. But hopefully you're sticking with it. All right. The input voltage V1 from the sensing system. Right. Okay. So now what we need to do. We know that we've got, this is 2 volts, and we know that this voltage is 0.7 volts. So we start at 0, and then we go up by 0.7. So now we're at 0.7, and then we go up another 2 volts. So then we're at 2.7 volts. So 2.7 volts is the answer. Let's see if we can express that as a formula. Okay, so V1, which is V1 is V in this particular case. V1 is V in, right? And so V1 is going to be the sum of the voltage between the base emitter, that's the 0.7 volts, plus the voltage that's dropped across the base resistor. So I can write it like that. You don't have to write it like that. If you just put the numbers down, I think it's pretty obvious as well as to where you've got your answer from. So that's going to be 0.7, and we said that was 2, and then so that's 2.7, so the answer is 2.7 volts. Okay. State the new values of V2 and V3. Let's have a look. What is V2? V2 is that. Okay, so is 0.7 volts. V3 is this one, VCE. So that is when the lamp is switched on fully, and if you remember, when the lamp is switched on fully, basically the switch is closed, so then that VCE or V3 is going to be 0 volts, so 0 volts. Final part of the question now. Complete the circuit by adding a suitable light sensing circuit, and my recommendation to you now is you just need to memorize some useful circuits, and I'm just going to draw it out, and you just need to memorize this one. We can trace through it and think about why it works, but you're best off, to be honest, you're best off just memorizing this one, because it's so common and it's going to be useful to you in your project work and whatever. So there we go. All right, there's the solution. Now they want the lamp to come on in the dark, so we need an LDR. Now a couple of students, they drew what do they draw? Thermistors, say, which don't detect light. So you need an LDR, a light dependent resistor, and you need it as a potential divider, because you need to you need to have a voltage which is going to be applied here, the input voltage, which is then going to then hopefully sufficiently bias that base emitter junction and push sufficient base current in, which then can be magnified by the gain, which will then have the lamp running at its full rated 180 milliamps. So we need this potential divider. So we need a fixed value resistor. We need an LDR. Now, which way round should they be? LDR on the top or on the bottom? Well, it needs to go on the bottom, and the reason for that is that if you consider how resistance varies with lux, or measurement of light, if say that is bright light and then that is dark, okay, so we're in light and then we're in darkness there, that the resistance is going to be something like that. Okay, don't worry about whether it's straight line or curve, but it's just going to, as it gets brighter, the resistance goes down. As it gets darker, the resistance goes up. So remember, when it gets darker, this resistance is going to be big. I don't know what it's going to be, but let's say it's going to be like 10k, and let's say we used a 1k resistor just as an example. Okay, so when this is 10k, this is it's 10 times more than this one, so there's going to be 10 times more voltage dropped across this one. So then you're going to have like close to 6 volts applied there, so that's going to be just fractionally over 5 volts there, and we're going to have like 0.7 volts there, and the lamp's going to be on. If, however, say you were in bright light, so then the resistance of this goes down. Let's say it goes down to say 1k, just as an example. I don't think it would, but if it went down to 1k, then that's going to drop so that then you're going to have like just 3 volts there, say. Okay. Now, in actual fact, of course, if you did have 3 volts there, then probably your transistor would still come on. So it might be better that, say, let's just change that one to say 10k now, then in bright light the majority of the voltage would be dropped across here, very little would be dropped across here, and therefore then it's more likely that the switch is going to go off. Now there are some issues with this sort of circuit which we're not going to deal with in this video, but having a transistor loading this potential divider is not a great idea. Okay, but more about that maybe another time. Hope you found that video useful. Maybe some of you are going to have to watch through a few times. I do strongly recommend you don't skip that bit, because you need to understand that. You do need to understand this. You need to understand the principle of biasing of a diode junction, or the base emitter junction in a transistor as well. If you're one of my students, if you've got any questions, just ask me when I'm back. I'm currently isolating at home, yeah, obviously I'm perfectly okay. I'm tested okay, but I have to stay at home for 10 days. Right, be seeing you soon then. Goodbye.